that single proton, because a hydrogen's only got one proton in the nucleus, and then we had multiple different orbitals that were available to the electron that belongs to that hydrogen. And so we had the ground state orbital, and then we had these different excited state orbitals, right? And so your electron sits over here in the ground state normally, but say you exert some force on it, maybe it absorbs a photon or whatever, it can be promoted to an excited state. It can be promoted to either one of those, and when it falls back down to the ground state, energy is released. The same way that when those two charges are allowed to approach each other, they go to a lower potential. In the hydrogen atom, if an electron is in an elevated state and it falls back down to the ground state, it releases energy as light, right? So we're going to get to look at this system very closely today. These are called gas discharge tubes, and what you've got inside that glass tube right there is a cloud of hydrogen gas. We're going to run a current across that cloud of hydrogen gas, and what's going to happen is that electrons are going to fall onto these hydrogen atoms, and they're going to start off at some excited state orbital, and then they're going to fall back down to the ground state or to the second excited state, or the whatever excited state it is that they fall to. And when that happens, discrete lines of emitted photons are going to be observed. You're going to see that when you look at this hydrogen discharge tube with your scope, that a series of very thin, narrow bands are observed for the emission of hydrogen. That is an example of what is called discrete emission. I don't know if I spelled that correctly. We're also going to see an example of what's referred to as continuous emission. Go ahead.
Can you say what discrete emission means?
It just means that there's only certain wavelengths of light that are emitted. Like you'll get emission at 550 nanometers, and your emission spectrum will show a peak right at 550 nanometers. But down here at like 560, you're not going to see anything. And so in discrete emission, you'll have a graph that your spectroscope provides you. You'll have intensity on the y-axis, and you'll have wavelength on the x-axis, and you'll run from, say, 400 nanometers to 700 nanometers. I think it actually runs 3 to 8. And for the hydrogen, you'll see specific lines from that emission. You'll only get emission at those lines, right? That has to do with the fact that only photons that have the energy corresponding to the differences between the initial state and the final state are emitted by that substance. So in this, we're dealing with specific electronic transitions from orbitals that are separated by an absolute distance. This happens for certain species. This discrete emission. It happens very readily for species in the gas phase because their energies are not coupled to the energies of any other systems, any other matter. In the solid state, some different stuff happens. And one of the things that we're going to look at is something called black body radiation. So, oops. It's my mom. You get black body radiation, and black body radiation is how we name the light that comes off a piece of matter that is really hot. So matter gets really hot, you know this, you've seen a fire, it starts to emit light. The hotter it gets, the more energetic that light is that's emitted. We're going to see an example of this when we kind of look at our flame over here. What's happening in that black body is the following. The electrons the electrons are moving from excited states to ground states, but it's not as absolutely defined the energies between the two states as it is in the hydrogen atom. In the hydrogen atom, the energies between these states, there's large gaps, and you only get photons that correspond to the distance between those gaps. In a black body, I guess the best way to draw this, in a black body, the differences in energies between the orbitals, the absolute magnitude of the distance between those the energies in those orbitals is smaller, and so you'll get many transitions from different excited states to different ground states. And because there's so many different transitions available, your spectrum will end up being broad and covering a large range of wavelengths. This is called continuous emission. It's almost safer to think of it as in terms of the thermal energy that is delivered to that black body is exciting the electrons and is just bouncing them around like crazy inside that material. And so these electrons get heated up, they're moving back and forth very rapidly, and they generate an emission of light. So let's go back to that little that image that we drew in section of the electromagnetic field. So the electromagnetic field is usually driven as a sine, or drawn as a sine wave, and we have, you'll see the E field is perpendicular to the B field, and it oscillates up and down. And so what this represents is a change in, let me turn this thing off, a change in the pull on a charged species. So an electromagnetic field, what a field does is it exerts forces on species that have, what an E field does is it exerts forces on species that have charge. So a charged piece of matter, if a field hits it, say I've got an electron over here, as this field passes by the electron, at one moment, the field will exert an upward force on the electron. The next moment, the field will exert a downward force on the electron. And then when you get back to the next peak, it'll be exerting an upward force. And then as the wave passes, it'll do a downward force. So if our E field is a sinusoidal field, then what it does as it sees a piece of matter is it exerts these forces that shift direction and cause that electron to move. So how do fields get generated? If I wanted to get have a sinusoidal electromagnetic field, how might I be able to manufacture that? All right, so I've got an electron right here. Imagine that I got a proton and I stick it right on the end of my marker. I got a proton right here. This proton is sitting at this position. The electron's getting pulled by it, right? What happens if I move the proton up here? Now the electron's getting pulled upward, right? What if I move the proton down here? Now it's getting pulled downward, right? So if I had a proton on the end of this stick, and I started moving it up and down, just shaking it, this thing's gonna feel a sinusoidally shifting pull, right? One minute the pull's going to be up here, the next minute the pull's going to be downward, and the direction of those forces is going to change in a sinusoidal fashion. Isn't that what I just said that the E field does? A sinusoidal E field? And so what I'm trying to tell you guys is that fields are generated by moving charges. When you have charges in a substance and those charges are moving around, the fact that those charges are moving generates fields that can be felt by other charges that are separated by a distance. So that's what happens in a radio antenna. you've got a radio antenna, you've got some metallic conductor, and it's got positive charges and negative charges all over it. And it's tuned so that those charges can be driven with certain frequencies, and so those charges are forced to move up and down with the appropriate frequencies, and that generates fields that are sent off in space and are picked up downstream by some other appropriate conductor. So we saw that we thought of this in terms of the discrete emission and absorption that happens with the hydrogen atom. You absorb a photon, your electron gets promoted up here, and as the electron moves back down, it releases that photon energy. But basically, any moving charge, any charge that's moving around and changing its velocity exerts electromagnetic fields. So today, in terms of this kind of a system, we have our light bulbs. Those light bulbs have a conductor that has some resistance. We run a current through it. That conductor gets really, really hot, right? When it gets really, really hot, its electrons start moving around like crazy, and it emits a big, broad spectrum of light. These lights up here, these fluorescent lights, do a couple of things. There's a charge that's shipped through a certain body of matter that heats that up and causes it to emit kind of a black body spectrum. But in addition to that, the tops of these bulbs are coated with mercury, and the mercury actually absorbs some of the photons that are emitted by the other body, and it promotes the mercury electrons up to an excited state, and when they fall back down, they emit a discrete spectrum. And so these lights are going to have black body spectra plus discrete emission like you have in the hydrogen. We also have light emitting diodes that we're going to look at, and light emitting diodes are examples of electrons that have been promoted to a single orbital falling back down to a single low state orbital. So you got a single high energy orbital and you got a low energy orbital, and electrons are pumped up to the high state orbital and they drop back down to the low state orbital, and when they do, they emit only discrete frequencies of radiation. So you're going to be able to look at those. We also have over here several salt solutions. So we've got strontium nitrate, barium nitrate, sodium nitrate. What do all of those solutions have in common? They all got nitrated. So nitrate's a negative ion, strontium, barium, and sodium, those are positive ions, cations. And you're going to see that when you take those ion solutions and you dip them into a flame, you're going to get different colors of emission from each of those solutions. So you're going to be asked to think about why that is the case for those systems. Real quick demo. Who borrowed the glasses from me? I'm going to steal these away from you just for a second. What did we say about the relationship between high energy light and low energy light? Blue, red. Which one's high energy? Which one's low?
Blue is high and red is low.
Blue is high and red is low. So if we have our spectrum here, and we've got like the 400 nanometer side over here, and we've got the 800 nanometer side over here, the 700, 800 nanometer light is red, and the 400, 450, 500 nanometer light is blue. So blue light, shorter wavelength, is higher energy than the red light, and that can be easily determined by looking at the equation E is equal to hc over lambda. Because lambda is in the denominator, the smaller lambda is, the larger the energy is for that photon. So, real quick thing I want you to look at, just because it's kind of cool, hopefully it works in this lab, it worked in the last one, is what happens when I adjust the oxygen on my Bunsen burner. Pay attention here, because you may end up lighting the Bunsen burner in your experiment, and people with long hair or loose clothing, get rid of the loose clothing, tie back the long hair before you go anywhere near the Bunsen burner, okay? All right, so a couple key points. When I light the Bunsen burner, The second I turn this on, gas starts to pour out of that thing. And if I were to sit there, if I were to turn this thing on and count to 40, 20 even, and then come over here with my, what are these things called again? Flints. Thank you. This vocabulary that I just lose. If I were to let this thing run for a long period of time, or even just a short period of time, and then come over with my flint and light it, I might have a whole cloud of gas sitting inside this thing. I actually had a student one time in a bio lab that we were doing, stuck their Bunsen burner on and turned on the gas and got distracted, did something else for a couple moments, came back and lit it, and we had a flame that went all the way to the roof and almost scorched the top of the roof of the building we were in. So the point that I'm trying to make is, turn your gas on, light it right away. Don't turn around and wait for a while. Down here on your Bunsen burner is an adjuster. And what this adjusts is how much oxygen is being allowed into the mixture. So,
Hi. This is the wrong room, sorry.
okay. So, did you guys remember the conversation we had about combustion? We said that combustion was driven by oxygen, right? Oxygen is this really like electron-hungry substance, and it comes in and it starts stealing electrons away from anything that's weaker than it, provided that it's got the opportunity. So, the more oxygen I allow into this gas mixture, the more combustion I'm going to get. Let's see how that plays out with the flame. So, turn this guy on, try to light it right away. Now here, I've got all of the oxygen ports completely open. What colors do you see in the flame? Mostly blue, right? Sometimes this works, sometimes it doesn't. As I close it off, it's not going to work so much with this one. Normally, when you start to choke the oxygen on these things, you'll see a lot more orange in the flame. So you put more oxygen in it, it gets really blue, and as you back the oxygen off, as you start to starve it, it gets orange. You see how the tip of it's orange now? Can you guys see the very tip? Yeah. And so I've got my hand around it, and I'm trying to prevent the oxygen from coming in, and so the intensity of the combustion has dropped, and the color of the emission has redshifted. And then if I let more oxygen in, it should become more consistently blue, although there's still a lot of orange in there. It worked really great in the next room over. All right, so what you're going to be doing with this station is you'll be wetting the tip of the spatula with some of this material, and you'll throw it in the flame, and you should see that the different solutions have different emissions when the matter that's in them is subjected to the flame. Different colors of emission. So what we're going to be doing, you've got three mechanisms that allow you to observe data for these systems. You've got your eyes. You've got these handheld spectroscopes that have diffraction gratings that break the emission apart into its component wavelengths and allow you to look at each wavelength individually. And you have a computerized system that collects the light in a fiber optic cable and then gives you a readout on your computer screen. So each of these stations, you're going to observe the emitted light from whatever the system is that you're observing with your eyes. You're going to record color. You talk about the colors that you observe with your eyes. You're going to look at the scopes. The scopes, you're going to record the color, which will also be evident, and the wavelength that the scope tells you is being observed. And then you'll go to your actual computer spectrophotometer, and the computer is going to read out for you a graph just like this for each of those sources, where you have the wavelength on the x-axis and the intensity, the magnitude of the peak on the y-axis, and you're going to capture that image. You should redraw every graph inside your lab notebook, including labeling the axes and approximating and showing the actual peaks under the wavelength that they are observed at. Also write down what colors you see and cross-check the data that you get from the handheld spec with the data that you get from the computer spec. All right, I think that's enough. So let's pair up with people. Backpacks under the seats, let's clear off the aisles a little bit. There's gonna be a lot of stuff on the bench tops today, and we don't wanna be knocking stuff over. And let's get started.